more difficult than the last unit, although the last unit 1 was kind of tricky. But the first 2 units of physics just are. And there are a lot of heavy problem solving. Even if you're really good at math, they can be challenging because you've never applied math this way. You've never applied it in very real situations. So it's part of what I love about physics is it actually gives you a reason for learning math. And you begin to realize why you've learned all this stuff the last 7, 8, 9, 10 years of your educational careers. So again, lesson 2.04. I put a couple of formulas up on the board we're going to need. Notice we're going to go back to, these should look familiar from unit 1. A distance formula with initial velocity time. Acceleration is gravity, because we're dealing with, in these problems we're going to be dealing with vertical and horizontal motion. In vertical motion, the accelerant is gravity, unless there's another accelerant added to it. But for most of our study, it's going to be just gravity. And then simple formula, distance equals velocity times time, or velocity equals distance over time, which is the same formula reorganized. We'll use those 2 formulas throughout this lesson. But the key to understanding lesson 2.04 is to realize that in the prior lessons, 2.01 through 2.03, basically we've been breaking apart motion, force that's applied at an angle, and we've been calculating its vertical and its horizontal components. And this is kind of a backwards look at that, because we're looking at, in this lesson, we're given a component of motion, a component of velocity as a component of motion in one direction, and problem solving depends on us breaking that down into its 2 individual components, because the vertical component and the horizontal components of motion separate. They act separately on an object and somewhat independently too. In the end, there's a resultant, but they have independent action on any given object. So that's the key to understanding this, is you have to break it down into its vertical and or horizontal, and in some cases both. I'm going to work problems off of the worked examples, so download those, pause the video and download those so you can read the examples. I have a little more room today because I'm in my classroom at UCCS, so I'm not on my little tiny whiteboard in my house, but I'm still not going to write up the questions because that's entirely too much work. So on the worked examples, you can see I've worked, you'll see this exact document in the course stream. I'm working problem 3 because it's where it starts to get a little bit more challenging. It says a projectile travels in the horizontal direction at a velocity of 200 meters per second. So I'm just going to note that with an array. Horizontal means parallel to the horizon. We know that. There's no angle here. It's just in this situation, the force is applied parallel to the horizon. At 200 meters per second from a cliff that is 200 meters high. So I'm just going to make myself a little drawing here of a cliff that's 200 meters high. I may not even need that, and maybe you don't need those kind of supports for your own problem solving, but I need those visual aspects just to remind me where I'm at in a problem, so it's a good idea to draw some pictures. And the question is, after how many seconds will the projectile reach the ground? So the projectile's thrown in a horizontal motion, but even though it's thrown in a horizontal motion, gravity is going to start to act on it, and it'll eventually hit the ground. And it wants to know, the one thing it wants us to find is how many seconds will it take to reach the ground. So honestly, I don't even need this 200 meters per second, because that has no effect on the vertical drop. Gravity is what's going to control that. So I'm going to use this formula, D equals VIT plus 1/2 G in this case, because I'm dealing with gravity, so my acceleration is going to be due to the force of gravity. As I think I showed you in Unit 1, initial velocity is almost always 0, and that's the case here because it's applying full 200 meters per second horizontal force, but that's not applying any force up or down. It's directly horizontal, so parallel to the horizon. So the initial vertical velocity is 0. So then in a sense that all goes away, and I only need this part of the equation, which is usually the case. It's rare to have an initial velocity this early in the study of physics. Eventually you'll get to those trickier problems that involve more components of motion that are actually more realistic. These aren't that realistic, but in order to begin the study of something new, it's necessary to kind of simplify things so that you can see conceptually what's happening before you really turn up the heat with complexity of problem solving. So what do we know about this? We know the distance is 200 meters. And you'll notice I don't always put the units in my problems, and probably there are teachers that disagree with that, but it's a good way to check your arithmetic, I suppose, to put the units in, but it'll all come out in the wash. But it is a good way to check your arithmetic to see if you're applying things correctly. The gravity I know is 9.81 meters per second squared. So I guess I'll go ahead and I'm going to put the units in for now. And then the time we don't know, but we know it's in seconds, so that's going to be seconds squared, which eliminates this second squared, and that's kind of how the units begin to come out in the wash. So let's do the calculations. And I'm actually not going to do the calculations. I did them ahead of time, and they're in the worked example. I trust that you know how to do the calculations. But when you do all this, you take 9.81 divided by 2, divide that product into 200. You should get about 40.8 is the time squared, and that would be seconds squared. We'll go ahead and put that there. And you know, and sometimes this is where people mess up. They forget that we need to take the square root of time squared in order to get time. So I take the square root of both of these. I'll go ahead and point that out because that is a fairly common mistake. And we should get somewhere around 6.4 seconds for the time. And that is the answer to this problem, 6.4 seconds. Sometimes you might get, because most of the questions have multiple choice answers, and on occasion you might be off by a decimal place or two. Don't worry about that. It probably has to do with where you rounded, and it has something to do with significant digits, which I don't spend a lot of time covering significant digits. I'm not going to launch into a detailed explanation of that, but that could cause your numbers to be slightly off, so you're going to pick the number that's closest to your answer. Usually you're going to get right on, but on occasion you may run into that, just so you know. So that's it for that problem. Now I'm going to look at problem 5. So I guess I should have put that up there. This problem 5 off of the worked example set. A worked example, by the way, is just a static worked out problem that has the answer to it, so you can see the process and the answer. It's just a scaffold to help you learn, and then you're able to go work similar problems for a while you refer back to that worked example, and then eventually you can work those problems without the worked example or any kind of help. That's the idea. So with these more difficult problems, I decided to include worked examples. Problem 5 is a two-parter. A swimmer runs over a horizontal diving board at a speed of 0.95 meters per second. So I'm going to draw let's have a green diving board. So I'm going to draw that at 0.95 meters per second. So we know diving boards are horizontal, so that's a horizontal motion. That's really hard to see, isn't it? So I'm going to put it in black. 0.95 meters per second. Hopefully that's a little easier to see. Yeah, it is. 2.0 seconds after she dives, so we have a time of 2.0 seconds. 2.0 seconds after she dives, she hits the water. What was the height of the diving board from the water surface, and how far from the board was the swimmer when she hit the water? So we have two problems to solve, and one of them deals with how far she was from the board. So if she jumps off the diving board, then her motion is the same as in the last problem. It's going to be kind of parabolic until she hits the water. So there's going to be this vertical distance, and there's going to be this horizontal distance. So for the vertical distance, we're back to this formula, and gravity is our accelerator. So I'm just going to pop over here and go ahead and work out that part because we have everything we need to know. We don't know the distance. We have our initial velocity, just like the last problem, this 0.95 meters per second. Since she's initiating it off of this horizontal diving board, it's going to be initially horizontal completely. And the only thing that's going to impact the vertical is gravity. So in theory, if we were in space where there's no gravity, if she ran off the end of the board, she'd just keep going that way. Gravity is what causes her to come back down to the Earth's surface. So the initial velocity then in this equation is 0, so we don't need that first part. Gravity is 9.81. When you don't know it, you always do 9.81. Sometimes the problem will give it to you. And then time, in this case we do know, so this one's actually easier than the last one. I didn't put units in. Again, putting units in is a good way just to make sure you're doing the arithmetic correctly. But I worked these out ahead of time, so I know I did the arithmetic correctly. And when I do all that calculation, the answer I get is 20 meters. I think it was 19.9 something something, but anyway, it rounds up to 20 meters. And that's all there is to that. So the vertical distance of the board is 20.0 meters. Now we need to find the horizontal. Well, the horizontal component is completely independent of any of this. We know its hang time, how much time it stood in the air, so I can use this simple velocity formula. And we can use this easy one because this is not very much time. There are more complex formulas to calculate this type of distance, but they're not necessary in this case because it's such a short span of time. So we can use this simple formula, and we are finding distance, so we'll use this one. Change colors just so you know. We'll go to blue. So distance equals velocity times time. Our velocity was 0.95. This time I'll use the units. And then our time was 2.0 seconds to give us our distance. Distance should be in meters, and we'll notice the seconds cancel each other out. You treat variables, or not variables, you treat the labels just like you do any other algebra equation, so they cancel each other. 0.95 times 2 gives me a distance of should be able to do that one in my head, 1.9 meters. So that's the two-parter. 20 meters distance or height of the board, it's a tall board, and 1.9 meters from the base of the diving board is where she landed. And that's it on that one. So see again, vertical components, horizontal components act independently. And when you realize that and you break them up, these problems aren't that hard. But when you don't know that, when